We have a beam of mass M here, center line here. It's an unloaded beam that balances on the center line if it's a uniform beam. Meaning that the center of mass is on the center line. We put a mass M on the beam, and we find that the balancing point moves over to here, a distance x from the center line. The mass M is a distance r from the center line. Given the value of x, can we find the mass? In other words, if we have a beam that's balanced, and we put a weight on one end, the balance point moves. Can we find the mass M in terms of the mass big M of the beam, the distance x, and the distance r? Well, if the beam is balanced, it's not accelerating in the, there's no rotational angular acceleration. So if it's balanced, then that torque is zero. Now the torque produced by a beam of mass M at a point distance x from its center of mass is mg times x, because the mass of the beam acts like it's all concentrated at the center line as far as producing torque around a point off of the center line. Center mass is a balancing point. The unloaded beam balances at its center line, so its center mass is on the center line. Okay, so for the beam mass system, net torque zero. You have the beam, you have the center line, you have the mass, you have the distance r, you have the distance x. The net torque is the torque produced by the beam on an off-center balancing point. And that torque is the mass of the beam times the distance of the center of mass from the balancing point times acceleration of gravity. Mass of the beam times acceleration of gravity times this distance gives you the torque produced by this force. The weight of the mass, mg, at distance r from the center line produces a torque mg times the distance of that mass from the balancing point. And the balancing point is at distance x from the center line, mass is at distance r from the center line, so the mass is at distance r minus x from the balancing point. So we have torque mg times r minus x. And it's a negative torque. This is a positive torque, tends to rotate in the positive direction as it's drawn. And this force produces a negative torque, a torque in the clockwise direction. So we have this net torque. If the net torque is zero, then mg, well, this expression is equal to zero, and we easily solve this expression for little m. And simplify it. We have a g here that divides out, so we end up with mx over r minus x, big M x over r minus x, and there it is. Now, in the case of this, I estimated that and I know the mass of the beam is somewhat less than 100 grams. It's more, I think it's around 90 grams. I estimated that the center mass of the domino was about 12 centimeters from the center line. And when the domino was placed on the beam, the balancing point moved about 2 centimeters. If you put that information in here, you get a domino mass of about 20 grams. So my estimate was actually fairly close. But not showing off about that, that's just maybe dumb luck on my estimates. But there it is. With refinement, you can weigh something fairly accurately using this kind of setup. Okay, shifting gears a little bit. We have a pulley, and it's got a significant mass. The pulley is basically a disc with some grooves in it, constrained to rotate about its center. And the moment of inertia of the disc is 1/2 big M R, big R squared, where big M is implicitly the mass, and big R the radius of the disc. We have two masses, M1 and M2, hung from different sides of the pulley. Okay, the mass M1, of course, experiences a force of gravity, M1G, mass M2, force M2G. And each of these forces tends to produce a torque. This force effectively acts right here, producing a torque of M1G times R, moment arm times the force. This one, the torque of M2G times R. This torque is positive, this torque is negative. So we have a net torque, M1G minus M2G, M1G times R minus M2G times R. We have a total moment of inertia of the disk, which is 1/2 mr squared, plus m1r squared, because this mass has exactly the same, well, its moment of inertia is the same as if it was attached right here on the wheel, and this one similarly. So the moment of inertia is going to be m1r squared. The moment of inertia of this one is m2r squared. So there's your moment of inertia of the total system. Okay, now I've already said everything here. We then find that the angular acceleration is equal to the net torque divided by the moment of inertia, which we know. And here's your net torque, and here's the moment of inertia. And we just rearrange this slightly. We factor a gr out of the numerator, and we end up with this expression. In a special case where we can regard the pulley as massless, in other words, a pulley of mass that's negligible compared to the masses of the hanging weights, this expression reduces down to this. Okay, and we can see that we remove the I disk here. We can factor out an r squared from the denominator, and big R divided by big R squared gives us an r in the denominator. So that's about it. The acceleration of m1, not the angular acceleration, the acceleration is equal to the radius of the disk times the angular acceleration. This is because the rope while it's on the disk, if we assume, and we implicitly do, that the rope isn't slipping, a point on the disk moves with angular acceleration alpha. So a point out here on the rim of the disk has acceleration along the arc equal to r times alpha, definition of a radian again. And that's the speed with which the rope is moving on and off of the disk, which means that's the acceleration of each of these masses. So there it is. Now that's the magnitude of the acceleration. Well, actually that is the acceleration. If we regard this direction as positive, in other words, this direction of rotation. So there's the acceleration of mass m1. Acceleration of mass m2 in space will be equal and opposite, because one mass is going down, the other mass is going up. We could also analyze this using methods that we had earlier. If the moment of inertia of the disk is negligible, then you just have a system consisting of mass m1 and m2, and total mass of that system is m1 plus m2. The net force on that system is, if we regard the direction is positive, if this mass is descending, then the net force is just m1g minus m2g, and that's straightforward. So the acceleration is what you see here, net force m1g minus m2g divided by the total mass, m1 plus m2, and we get the same expression we had here. So if we wanted to just get this, we wouldn't have gone to all this trouble of analyzing it if there was a significant moment of inertia in the disc, in the pulley itself. But this is very handy, and we should understand how all this comes about. Now we can ask a few questions. If the mass m1 descends a distance h from rest, what's the change in the potential energy of the system? Well, this mass descends a distance h, so its potential energy will drop by mgh. The potential energy of this mass will increase by m2gh. So that the change in potential energy is the negative m1gh plus m2gh, which is just negative quantity m1 minus m2 times gh. So that's our change in potential energy. If there's no dissipative force, if the gravitational force is the only force acting on the system, then that's going to be equal and opposite to the change in the system's kinetic energy. So we could immediately calculate its final kinetic energy. If it starts from rest, it'll just be equal to the change in the kinetic energy. And we could then set the expression for kinetic energy, 1/2 total moment of inertia times omega f squared, equal to the change in potential energy, which is m1 minus m2 gh, actually to the potential energy. That's equal to the change in potential energy minus the initial potential energy. So we immediately get the expression for the final angular velocity. Okay, now, question, what is delta theta if the mass descends distance h? Well, if the mass descends distance h, then the amount of string that wraps around or unwraps from the disk is going to have length h, which means the disk has to move through angular distance that corresponds to an arc distance of h. And that angular distance is just h divided by the radius of the disk, by the definition of a radian. So your delta theta is just h over r. That's the arc distance. Now we're implicitly assuming that the rope doesn't slip on the disk. Okay, so now the question is, how much work is done by the net torque? Well, if we understand the analogies between rotational and straight line motion, just as the work done by a constant force moving through a displacement in the direction of the force is the product of the force and the displacement. In other words, the work is F times delta S. Just by analogy, delta theta is analogous to distance or displacement, and tau net is analogous to force. Now this is easily derived, but if you remember it by analogy, it's not a bad way to remember it. You want to go a little deeper than that, but this will get you by. So the work is torque times your change in angle, which is torque here, there's your torque, times your change in angle, which is h over r. And you simplify that and you get m1 minus m2 times gh, which agrees with this expression. Of course, I have the m1 minus m2 factored out here, but it could be factored out here as well. Well, there it is factored out. So this agrees with this. I guess I could have looked at my arrows. Okay, so in either case, the change in kinetic energy is the work done on the system by the net force, which is equal and opposite to the change in potential energy. And then to find the final angular velocity, there are various things we could use, but this gets us. So we use this to get the relationship I referred to earlier, and we get the final angular velocity, expression for the final angular velocity. We can get that expression by analyzing the motion given the acceleration. We can get that expression by analyzing the change in potential energy, or the work done on the system. All these alternatives are available to us. Okay, one more thing. Yeah, okay, this will work. Okay, the conditions for equilibrium. Forces have to be in balance, meaning that the net force has to be, well, go in the right direction. Net force has to be zero, which means that if you add up all your forces, of course that gives you the net force, and the sum of all the forces has to be zero. Net torque has to be zero. If the net force isn't zero, you have an acceleration. If the net torque isn't zero, you have an angular acceleration. So sum of all your torques has to be zero. That summarizes equilibrium. Now you might see this written as the sum of Fx equals zero, the sum of the forces in the x direction equals zero, or sum of Fy equals zero, sum of forces in the y direction is zero. And if you got a z direction, you got that too. Don't think it's necessary to write all that. This condition and this condition imply these conditions, and these conditions are sufficient to the whole thing. But if you want to break it into Fx and Fy, you can do that. Okay, apply this to a uniform beam of mass m. So we have two balancing points here. They're not really balancing points, two supports. One at distance r1 from this end, the other at distance r2 from this end. You have a beam of length L, and of course the center line is at L/2, and as far as producing torque is concerned, the weight of the beam acts as if it was located at the center of mass. It's a uniform beam, so the center of mass is at the center. Length of the beam is L, center is at distance L/2 from either end. Now I used an analogy. I've got a 40-foot ladder out in the yard, and I can still pick it up and move it around. Can't move it as far as I used to be able to move it, and it's a whole lot harder to set the thing up than it used to be, and it used to be impossible, so it's even more impossible now. You need at least two people, and preferably two big people to handle that ladder. If you and I were carrying it, and I decided to be nice to you for one reason or another, I would grab the ladder closer to the center of mass and let you grab it out here. Now, a lot of people have had that experience, but maybe hadn't thought about it. Because the closer I grab it to the center of mass, the more of the weight I'm going to have to support. And the less weight you're going to have to support if you're further from the center of mass. So this support is going to have to support more weight than this one, at least the way I've got it drawn, because this support is closer to the center of mass than this support. Well, we can work out all the details. The sum of the forces is zero, so the force exerted on the beam by this support, F1, added to the force exerted the beam by this support, which is F2, has to equal the weight of the beam, mg. So, very simply, the sum of your forces is this F1 plus a negative mg, because that's down, plus F2 equals 0. I've got them in a different order there, but that's it. The sum of the torques also has to be 0. Now, see, from this equation, you don't know how the forces divide up between F1 and F2. All you know is that their sum has to equal the weight of the beam. If you take rotation into consideration, you can get another equation in F1 and F2, and now you have two equations that you can solve for both F1 and F2. Two simultaneous equations. Now, sum of the torques is 0. What are the torques? Well, the torques about the left end, and I should say these are taking these torques about the left end. Now, you don't have to take them about the left end. You could take them about the right end. You could take them about the center. It won't make any difference. You're going to get, your equation's going to look different, but it's going to be totally equivalent to the equation that I've written here using the torques about the left end. Okay, so the torque of this is counterclockwise torque, F1R1, distance, force. Here, F2R2, and this one is also counterclockwise. mg, though, gives you a clockwise torque, and mg times the distance from the left end is mg times L over 2. And so these two equations can be solved for F1 and F2. Now, I'm not going to do that. You can easily do it. I'll just solve this one for F1, plug that result in for F1 here, solve it for F2. More complicated case is this one. We have given information. Okay, we have cables, and we have some kind of a support here, some kind of support here. These cables are supporting this beam. Okay, here's our center line. We've got mg acting down here. We know that. This cable is attached at distance r1 from the left end. This at distance r2 from the left end. Now, I started with the idea that the sum of the forces is 0, because we know that's the case. What are the forces? Tension T1, well, we don't know what T1 is. We don't know, but we do know at what angle it acts. It acts at an angle θ1, which is the arctangent of h1 over r1, because h1 is this height, r1 is this. Similarly, over here, this angle is the arctangent of h2 over, and I said h2 over r2, and that's totally wrong. h2 over L minus r2. And that's going to complicate the expressions. All my R2s have to be replaced by L minus R2. And that's going to get pretty messy. So I'm going to write it in on top of R2, L minus R2. And down here where I have R2s in my denominator, these have to be L minus R2, and this should be R2 here. Okay, so those are going to be a little hard to read. We don't need these relationships, okay? The cosine of θ1, yes, would be the cosine of the arctangent of h1 over r1, and you should know how to do that. But let's just observe, we've got a right triangle here. The cosine of, put this in parentheses, you don't really need it. The cosine of θ1 is just the hypotenuse divided by r1. The hypotenuse is the square root of r1 squared plus h1 squared. So there we have it. Okay, and the sine of θ1 is just this side over the hypotenuse, h1 over the square root of r1 squared plus h1 squared. T1 is therefore need to look more closely at what I'm looking at. this should be R1 squared. And this should be R1 squared. Losing track of where I am with my subscripts and not really thinking that clearly about the expressions and what they mean. So let's correct it. This is R1. This is R1. The L minus R2, well, that's what we should have here, here, and here. And that requires some modification. So I'm going to stop this video, correct that stuff, and then do it with the right expressions on the board.